Jai Hind to everyone. Myself, Ravindra Kumar, Assistant Professor, EN Department, AKGEC Engineering College, Ghaziabad. Today I am presenting on the topic transformer in the subject Basic Electrical Engineering, for which the subject code is KEE101T. So, under this discussion, I will be discussing some various subtopics for this topic of transformer, like what is the working principle of a transformer, how to define the transformer, constructional features of a transformer, plus various types of transformers which may be classified on the basis of construction plus on the basis of their utilization, and finally the EMF equation of the transformer that will be discussed under this discussion today. So, if we see it, the various contents in this discussion, those are definition, we will discuss, definition of this transformer that we will discuss under this, working principle, construction, types of transformers, and the EMF equation of a transformer. All those topics will be discussed under this discussion. So, first if we see it, the definition part of a transformer. A transformer is a static device, that means there is no moving part in a transformer. It is a static device, and by means of this transformer, electrical power that is transferred from one circuit to the another circuit, and these two circuits for in which the power is transferred from one circuit to another circuit, those are AC circuits. Why it is so, that we will come to know later on under this discussion. Another thing, there is no electrical connection between the two circuits. They are, that means they are isolated from each other. That is also important point. Next is the desired change in the voltage or current that is obtained without any change in the frequency. Means to say, the frequency which is there at input side of the transformer for the AC supply, same will be the frequency of AC supply on the another side or the second side of the transformer. That means to say, there will be no change in the frequency level or value of frequency on the two sides. Since the two sides they are AC circuits, the frequency is associated with that, but frequency remains same on the two sides. Another important point, the working of transformer, it is based upon principle of mutual induction. That means the two sides, they are connected mutually with each other, and mutual induction takes place between the two sides, by the help of which power transfer from electrical power transfer from one circuit to another circuit or from one side to another side takes place with the help of mutual induction. So, this is basically the working principle of mutual induction. So, all these points that we have taken, they are covered under the definition of a transformer. So, if we see it with this diagram, what is this in this different things? This is the rectangular core, this one is rectangular core, all this is a rectangular core of the transformer, on which the two sides are wound. So, this is the primary side, this is shown here, primary winding or primary coil, having number of turns Np. N stands for number of turns and P for primary. So, Np represents number of turns on the primary side. Ip is the current on primary side, this is shown here with the symbol Ip. Vp is the voltage on primary side, which is applied by the help of AC supply. So, primary side means where we are connecting AC supply to this coil, primary coil or primary winding, that is known as primary side. So, that means what I will do, I will connect AC supply here, and the voltage of this supply is Vp. So, this is primary voltage applied to the primary side of the transformer, and this is the coil. This is known as primary coil or primary winding, and this side is known as primary side, on which is having number of turns Np on this side. Now, if we see secondary side, this is the secondary side having number of turns Ns. This is written here, secondary winding having number of turns Ns, and represents the number of turns, and S for secondary. Similarly, Is, this is the secondary current that is shown here, and Vs is the voltage at secondary side, since V is voltage and S for secondary. So, Vs represents voltage at secondary side. So, what happens when we connect this primary side with the AC supply having a voltage Vp, a current Ip, which is primary current, that passes through this primary side or primary winding, and due to this a magnetic flux phi that is shown here, that is established or that is developed in the core of the transformer. The path of this flux that is shown by this green line, dotted line, this is the path of flux in the core, and this flux is time varying flux basically, since AC supply is connected across the primary winding. So, due to this time varying flux, this flux is linking with both the sides, primary side as well as secondary side. Since both the sides they are wound, or both the coils or windings they are wound on a common magnetic core. So, due to this, this flux is linked with both the sides, and this is time varying flux. So, what happens, as per Faraday's law of electromagnetic induction, the EMF is induced on both the sides, which can be given as E1, which is the induced EMF on primary side, that will be given by minus Np d phi by dt. And similarly, the induced EMF on secondary side E2, that will be given by minus Ns d phi by dt. Now, E1 is the induced EMF on primary side, which is sinusoidal EMF. It is equal to minus Np d phi by dt, where Np are the number of turns on primary side, that already we have seen, and d phi by dt is the time varying flux linked with the primary side. And similarly, E2, that is induced EMF on secondary side, that is again sinusoidal EMF, it is equal to minus Ns d phi by dt, where Ns is the number of turns on the secondary side, and d phi by dt time varying flux linked with the secondary side. So, as per this, we have induced EMF on both the sides. Now, this induced EMF on primary side, that will be known as self induced EMF, since it is due to its own effect, primary effect, or that is why it is self induced EMF. But on the secondary side, the induced EMF E2, this is known as mutually induced EMF, since this is due to mutual effect or mutual induction effect of primary on the secondary side. So, E1 will be known as self induced EMF. While E2 is mutually induced EMF. So, that way on both the sides, primary as well as secondary side, or primary and secondary coil, induced EMFs are there due to it. Now, if I connect some load impedance here or load resistance here, anything it may be there. So, due to the completion of this circuit on secondary side, the current passage in this load resistance, secondary current Is, and when both the voltage and current are there on secondary side, that means electrical power is there on the secondary side. So, that way what we can observe or we can see, the power which is input to the primary side at this side, that power is transferred to this secondary side with the help of mutual induction or by the process of mutual induction, which is the working principle of transformer. Another thing which may be there, if I keep secondary side open circuit, if I do not connect any load resistance here, that means the secondary side is open circuit. So, what will be the outcome of it or what will be the result of it? Induced EMF will be still there on the secondary side, that is as per this equation that already we have seen, but no current will be there on secondary side, no induced current will be there on secondary side due to open circuit at secondary side. So, that time only the induced EMF will be there on secondary side, no induced current will be there on secondary side. That means, no power will be there that time at secondary side if secondary side circuit is kept open circuit. So, power transfer takes place when secondary side circuit is also closed circuit or complete circuit. So, if we see it further in detail all about this, that what is happening here, the working principle of a transformer that already we have discussed. So, if we elaborate it further, the basic principle on which a transformer works, that is Faraday's law of electromagnetic induction, and basically it is mutual induction, since in the secondary the EMF is induced due to mutual induction process from the primary side. So, this is mutual induction between the two coils or between the two windings of the two sides, that is primary and secondary side. So, the working is explained as the principle of mutual induction states that when the two coils on the two sides, they are inductively coupled, and if the current in one coil changes uniformly with time, then an EMF is induced in the other coil, that means second coil which is on secondary side, and this EMF can drive a current in the secondary side when a closed path is provided to it. That already we have seen here. If I close the secondary circuit by connecting some load resistance or impedance here at secondary side, then a current is also induced on the secondary side. But if no resistance or no load impedance is connected at secondary side, that time no current will go in this secondary side circuit, since it is open circuit that time. So, this is about this. When the alternating current flows in the primary coil, a changing magnetic flux that is generated around the primary coil, that we can see here. When this primary current, which is time varying current, sinusoidally varying current basically it is. So, when it is passing in the primary side, a flux around this coil that is developed, and the path of flux that is shown by this green dotted line in which is passing through the core, this is a rectangular core. So, that way this flux is developed or generated around the primary winding. Now, this changing magnetic flux that is linked to the secondary winding or secondary coil through the iron core. Iron is the material of this core, that is why it is iron core, and hence an EMF is induced in the secondary coil. That already we have seen by this method, that E2 equal to minus Ns d phi by dt. This is as per Faraday's law of electromagnetic induction, and E1 is also induced in the primary side, which is minus Np d phi by dt. Now, another important thing, this minus sign, what is this minus sign here, and similarly here, this is as per Lenz law. Since Lenz law tells us that the induced EMF opposes the very cause which is responsible for inducing this EMF. That means here, this change in flux which is responsible for inducing the EMF on primary and secondary side. So, this minus sign that tells us or that explains us that this is due to the reason that the induced EMF on primary and secondary side that will oppose the very cause which is the changing flux, time varying flux. It will oppose the time varying flux which is linked on the two sides. That is the due to it this minus sign is there. Now, other thing, if the load is connected to the secondary winding or secondary side, then this EMF drives a current through it, that already we have seen how it is so. The magnitude of this output voltage that can be controlled by the ratio of the number of turns in primary coil and secondary coil, that we can see. Since we have seen that E1 and E2, they are dependent upon number of turns on primary and secondary side. So, if I take the ratio of E1 and E2, I will get E1 upon E2 equal to Np upon Ns. So, the secondary EMF E2 that can be controlled by changing this turns ratio Np upon Ns or Ns upon Np, whatever we take it mathematically. By controlling this ratio, we can change the magnitude of induced EMF on the secondary side. That way it is there. Other thing, the frequency of mutually induced EMF on the secondary side, that is same as that of the frequency of alternating source which is connected to the primary winding on the primary side. Why it is so? The reason for this is very simple. We have seen that induced EMF E1, this is minus Np d phi by dt, and similarly induced EMF E2 is minus Ns d phi by dt. This is written here. So, from this we can see that induced EMF on the two sides, that is basically dependent upon rate of change of flux linked on the two sides. Now, rate of change of flux d phi by dt, which is linking on the primary side and with the secondary side, that is identical or that is same on the two sides. That is why the frequency of the induced EMF on the two sides, that is same, or in other words we can say whatever is the frequency of the input voltage supply, same will be the frequency of the output voltage which I will get at the secondary side, or in other words there will be no change in frequency on the two sides, that will remain, frequency will remain same. So, this is the elaboration of working principle of a transformer. Now, another important thing, a transformer cannot be operated on DC supply, that is very important. Why? That is very simple, we can say it. Transformer action does not take place with a direct current of constant magnitude. Since we know that DC supply, that is having constant magnitude and there is no change in the direction of DC with time. So, what happens? Because with a DC primary current, the flux produced in the core is not alternating, but it is of constant value or constant magnitude. Since flux phi, this is the flux, that is basically depend upon nature of this flux depends upon the nature of supply. If we are connecting AC supply, that already we have seen here, if we are connecting AC supply here on the primary side, the current which is passing in the primary, that is also AC current. So, due to this the magnetic field which is developed and the magnetic flux due to that which is developed around the primary coil or primary winding, that is time varying flux, this d phi by dt, that is there due to it. But in case if I connect DC supply here on the primary side rather than AC supply, then the current IP on the primary side, that will be constant current rather than time varying current or sinusoidal current. So, due to it a magnetic field and magnetic flux will be developed again around the primary winding or primary coil, but that magnetic field will not be time varying magnetic field and the magnetic flux due to that, that will be having constant magnitude rather than time varying flux. So, in case of DC supply, there will be constant flux rather than time varying flux, or in other words I can say d phi by dt will be 0 in DC supply, since it is constant flux rather than time varying flux. So, when d phi by dt is 0, then there will be no induced EMF on any side, that is primary side and secondary side, that we can see from the relation. E1 is minus Np d phi by dt and E2 equal to minus Ns d phi by dt. When d phi by dt is 0 due to DC supply connected on the primary side, so there is no question of induced EMF on any side. So, that time I can say E1 is 0 and E2 is also 0 in DC supply. So, same thing is elaborated here, as there is no change in flux linkage with the secondary winding, the induced EMF in secondary winding is 0. If another thing, if DC is applied to the primary, then there is a possibility of transformer core getting saturated. And when core saturation takes place, what happens due to this? The primary winding will draw excessively large current from the DC supply, and due to this transformer may get damaged or may get burned. So, the application of DC on a transformer should be avoided. So, that means transformer is working on AC supply rather than on DC supply. That is the important thing. So, that is why we have seen it already in the definition part, that a transformer is a static device by means of which electrical power is transferred from one circuit to another circuit, and that already we have discussed that these two circuits or these two sides, they are AC circuits or AC sides. So, since transformer cannot work on DC supply. So, this is about working principle of a transformer, that how it is operated on AC supply and why it cannot be operated on DC supply. Now, another thing, construction, that how the transformer is constructed. So, basically a transformer consists of two windings that are on two sides, which are also known as two coils, and a laminated steel core, that already we have seen. This is laminated steel core, this is this one. These coils or windings are insulated from each other as well as from the steel core. That means insulation is put on the coil or on the winding. A transformer also consists of a container for winding and core assembly, that is known as tank. That container is known as tank. Suitable bushings to take out the terminals of the windings, oil conservator to provide oil in the transformer tank for cooling purposes, etc. So, we can see here in this diagram that this is the core, laminated core of the transformer. These are the coils which are wound on the transformer core. So, this is one coil, this is primary coil, we can say this one is secondary coil or secondary winding, and these terminals of these coils, primary coil as well as secondary coil, they are taken outside with the help of bushings, that is shown here, this one, similarly this one. So, these are taken with the help of bushings outside, and this is transformer tank. Here it is oil conservator, and this is silica gel breather. This is used for checking the moisture content in the transformer oil. These are the pipes connected. So, this is the complete assembly of a transformer, and this transformer oil, that is having basically the two purposes. One is it is used as a coolant, means whenever losses are various types of power losses, they are taking place in the transformer. Due to that, heat is generated or developed inside the transformer. So, temperature rise takes place in the transformer. So, cooling is required for that purpose. So, transformer oil that provides that cooling, plus this is transformer oil also works as an insulator. That means, the different sub parts of the transformer, they are insulated from each other with the help of this transformer oil. That is why it works also as an insulator. other than that, in all the types of transformers, core is constructed by assembling or stacking laminated sheets of steel. That means the material which is used, that is steel, but we are taking laminated sheets of that material steel with minimum air gap or almost no air gap, we can say, between them, so as to achieve continuous magnetic path between those various sheets. The steel used is having silicon content and sometimes heat treated also, so as to provide high permeability and low hysteresis loss. So, by doing this, that means by having silicon content in this steel, we have low hysteresis lossage. Other than that, laminated sheets of the steel, they are used so as to reduce the eddy current lossage in the transformer. That means, if we are using solid core rather than laminated core in a transformer, that time more eddy current lossage will take place in the transformer. But on the other hand, if we are using laminated sheets in the core rather than using the solid core, that time eddy current lossage will reduce. That is the advantage by having laminations in the core. These laminated sheets, they are cut in the shapes as E, I and L to assemble the core. To avoid high reluctance at joints, laminations are stacked by alternating the sides of joint. This is also done so as to avoid the high reluctance at the joints. Now, if we see the types of transformer, so first we see on the basis of construction. So, transformer can be classified in two types on the basis of construction. One is core type transformer and second one is shell type transformer. They are the basically two types on the basis of construction of a transformer. So, first one is core type transformer. If we see it, in core type transformer, windings are cylindrically wound and mounted on the core limbs. The cylindrical coils have different layers and each layer is insulated from each other with the help of insulating material like paper, cloth or mica. Low voltage winding, they are placed nearer to the core as they are easier to insulate. So, this is about core type transformer. So, here we can see in this diagram, this is laminated core made up of steel material. This vertical part of this core, this portion, this is known as limb. Similarly, this is also limb, and this horizontal part of the core, this is known as yoke, Y-O-K-E, yoke. Vertical part is limb or leg, while the horizontal part is yoke. So, low voltage winding, that is placed first or that is put first or that is wound first on the limb of the core, and after that on low voltage winding we are putting high voltage winding outside. Why we are doing so? This we are having on both the limbs, same manner we are doing that low voltage winding inside, that means on the core first, and over that high voltage winding. This we are doing so in order to save the insulation. Since low voltage winding, that will be requiring less insulation from the core. So, for saving the insulation, we are putting low voltage winding first on the core, or we are taking low voltage winding first on the core limb, and over that we are putting high voltage winding. So, this is shown here, low voltage connection, LV connection means LV winding. This is shown by blue color inside, and HV insulation, this is yellow color, and HV winding, this is orange color or red color, that is shown outside. Magnetic lines of flux, that is shown this white line. So, this is core type transformer. And if we define it, this is about the construction of core type. If we define it, we can say the core is surrounded by the windings, or windings surround the core. That is the definition of core type transformer. Then next we have shell type transformer. This is again on the basis of constructional feature of a transformer. In this, what is there? The coils, that means primary and secondary coils, they are former, wound and mounted in layers stacked with the insulation between them. A shell type transformer may have simple rectangular or it may have a distributed form. So, here this is the core, this one is core, all this is core of this transformer, this is shell type transformer. So, here in this core we can see there are three limbs, one limb is this, second limb is this and third limb is this. Now, in this case the primary and secondary coils or windings, they are wound or they are put on the central limb, on this limb. On the outer limbs there is no winding, on this limb and on this limb there is no winding, that we can see. Now, this is primary winding, since V1 is the voltage on primary connected across primary winding and V2 is the voltage across secondary winding with the help of principle of mutual induction that already we have discussed in the starting. Now, what will happen here? The flux is developed around these windings and that is common magnetic flux, and this flux is distributed along this path, this is shown here, this path and this path. So, flux is developed in the central limb or middle limb and that flux is equally distributed on the outer limbs, which are two limbs, outer limbs. So, that is shell type transformer, this one. So, if we compare the two types or if we see the differences between these two types, shell type and core type transformer, so we can see it by this table. Shell type transformer, that is on the left side of the table, and core type transformer, that is on the right side of the table. In the shell type transformer, low voltage and high voltage winding, LV means low voltage and HV means high voltage winding, they are wound over the central limb or middle limb and are interleaved or sandwich type, that already we have seen here in this, that we have seen shell type transformer, that these two windings, primary and secondary winding, they are wound over the central limb or middle limb and they are of sandwich type. If we take the core type transformer, what is there? Half of the low voltage winding is placed over one limb and half over other limb. Similarly, other thing, low voltage winding is placed first over the limb of the core and over it high voltage winding is placed over both the limbs in order to save the insulation of the winding, that already we have discussed why it is so. Other than that, in shell type transformer, the flux in the central limb that divides equally and returns through the two outer legs, that we have seen already, that in this diagram we have seen it, that the flux which is developed in the central limb, that is divided equally in outer limbs. While in the core type transformer, flux has single path around the yoke and limb, that we have seen here in this core type transformer, that there is a single path for flux in the core, in this core type transformer. Other than that, in shell type transformer, interleaved or sandwich windings are used, while in the core type transformer, concentric coils or windings they are used, which are also known as cylindrical windings or coils. Other than that, shell type transformer that is used or preferred for low voltage and low power applications, while core type transformer that is preferred for high voltage and high power applications. Some more differences that we can observe in these two types, that we can see from the diagram also. In shell type transformer, there are three limbs in the core that we have seen, 1, 2 and 3. While in core type transformer there are 2 limbs only. That is another important thing. So, there is one window in core of the transformer in core type transformer, while in shell type transformer there are 2 windows here in the core of the transformer. That is also the important thing. Other than that, the maintenance, if we discuss or if we see, the maintenance of core type transformer, that is easier, but in shell type transformer maintenance is difficult and costly also. So, reason being, the windings are wound over the central limb, while in the core type transformer the windings are wound over the outer limbs. So, this is these are the various differences on the basis of which we can differentiate the 2 types, shell type and core type transformer. If we further see classification of transformer on the basis of purpose, secondary voltage with respect to primary voltage, that means. So, there are step up transformer in which voltage increases with subsequent decrease in the current in the secondary. On the other hand, we have step down transformer where the voltage decreases with subsequent increase in the current in secondary, or we can say in step up V2 is more than V1, while I2 is less than I1, and in step down V2 is less than V1 since voltage decreases here, but current increases. So, I2 will be more than I1, and the reason for this is that the product of voltage and current will remain same on the 2 sides. That means, V2 I2 will be equal to V1 I1. So, if voltage decreases, then there will be subsequent increase in the current, and if voltage increases, then there will be subsequent decrease in the current. That way we can see it. Another classification on the basis of type of supply, if we may have single phase transformer and we may have 3 phase transformer. So, single phase transformer is connected with single phase AC supply, while the 3 phase transformer that is connected with 3 phase AC supply. Another classification on the basis of their use, power transformer, it is used in the power transmission network and it is having high power rating, while the distribution transformer that is used in the distribution power network and it is comparatively have lower power rating than that of power transformers. Other than that, we have instrument transformers. These are used in relays and protection purpose in different instruments. So, that time they are known as protective transformer also, and in industry we use current transformer, this is known as CT in short, and potential transformer, that is known as PT in short. So, these current transformer and potential transformer, they are also known as instrument transformers, since what is there in these transformers, current transformer is used for measuring high current. So, this is just like for measurement of current, just like an ammeter. So, that is why it is also known as instrument transformer. And similarly, this potential transformer PT, it is meant for it is used for measuring high voltage. So, this is just like voltmeter. So, we can say it is also again an instrument transformer. So, they are the various classifications of transformer on the basis of different purposes or usage. Other than that, this is the last topic of this discussion, EMF equation of a transformer. So, in a transformer, when AC supply is connected to the primary winding or primary coil or primary side, due to this, the current in the primary winding, which is known as magnetizing current in the primary, that produces an alternating flux phi in the core of transformer, and that flux can be written as phi equal to phi max sin omega t, where this phi is the instantaneous value of the flux. and phi max is the maximum flux. Omega is the frequency and T is time. This alternating flux that gets linked with the secondary winding or secondary coil on the secondary side, and due to the process of mutual induction, an EMF gets induced in the secondary winding that already we have discussed in detail when we have discussed the working principle of transformer. Magnitude of this induced EMF can be found by using the following method. So, this is basically the derivation part for the EMF equation or the induced EMF on the two sides. So, assuming that N1 is the number of turns in the primary, N2 is the number of turns in the secondary, phi m, that is the maximum value of the flux in the core in Weber, and this is given by Bm into A. Bm means maximum value of flux density. This is basically B max, and A is the area of the core. Bm is maximum flux density, and A is the area of core. And F is the frequency of input AC voltage supply in hertz. Hertz is the unit for this frequency. So, if we say it, this is the flux wave that can be seen. On this side we have time axis, and on this side vertical side we have flux axis. So, this phi is phi max sin omega t. So, this is sinusoidally varying flux which is passing in the core of transformer, and this flux is linking with the two sides, primary as well as secondary side of the transformer. So, as we can see in this diagram, the flux rises sinusoidally to its maximum value phi m from 0. That means, from 0 here to this phi m value, maximum value, and time taken for this is T by 4, where capital T that represents the time period of this flux. Capital T is the time period of this flux wave. That means, for time required for completing one oscillation of this wave, it reaches to the maximum value in 1/4 of the cycle, that is in T by 4 seconds. Now, we know induced EMF per turn, that is given as rate of change of flux per turn as per Faraday's laws of electromagnetic induction. That already we have seen, that induced EMF is given by minus n d phi by dt on any side. So, the induced EMF for a n turn coil where phi is phi max sin omega t, that already we have seen here. So, E is given by minus n d phi by dt, that is this. So, by putting the value of phi in this equation, E becomes minus n d by dt, that means differentiation of flux that is phi max sin omega t, since phi is equal to phi max sin omega t from this equation. So, after taking this differentiation, it is equal to minus n into phi max into omega cos omega t, since the differentiation of sin omega t with respect to t is omega cos omega t, and this can be simplified as omega n phi max sin omega t minus 90, since sin omega t minus 90 is equal to minus cos of omega t, and this can be written E max sin omega t minus 90, where E max is the maximum value of induced EMF, and this is equal to omega n phi max, and omega is equal to 2 pi f, since omega is angular frequency which is equal to 2 pi f. So, that is why we can write E max equal to which is omega n phi max or 2 pi f and phi max. So, that way we got it. So, if we find the RMS value of induced EMF, that is E1, which is the RMS value of induced EMF on primary side, so that will be equal to maximum value of induced EMF divided by root 2, and this can be written as omega n1 phi max upon root 2, since n1 is the number of turns on the primary side, and that can be written as root 2 pi f n1 phi max, since omega is 2 pi f. So, by simplifying the relation, we get E1 equal to root 2 pi f n1 phi max, where E1 is the RMS value of induced EMF on primary side. Similarly, the RMS value of induced EMF on secondary side, that is E max by root 2, and this will be written as omega n2 phi max by root 2 as earlier, but now the number of turns are n2 in place of n1, since we are dealing with secondary side this time, and this can be simplified as again root 2 pi f n2 phi max. So, this is called the EMF equation of a transformer. So, in these two equations E1 and E2, we can see basically E1 and E2 they are dependent upon N1 and N2, since frequency of the induced EMF on the two sides, that is same, that already we have discussed why, and phi max is also same on the two sides. So, basically it is number of turns on the basis of which the induced EMF depends. So, further, if finally we find the ratios of transformer. So, from these EMF equations that we have derived in the previous slide of primary and secondary voltages of a transformer, and taking the ratio of these equations, we can write E2 upon E1 equal to K, where K is turns ratio, and this is equal to V2 upon V1, that is voltage ratio we can say, since it is in terms of voltages on the two sides, and it is equal to I1 upon I2, this is current ratio, since I1 and I2 are the currents on the two sides, and it is equal to N2 upon N1, that is again turns ratio, and basically this K, that is known as transformation ratio of a transformer. So, we can write the equation K equal to N2 upon N1, which is equal to V2 upon V1, which is equal to E2 upon E1, and that is equal to I1 upon I2. So, this is the ratio equation for a transformer. So, this is all about this transformer, and in the next lecture we will be discussing about ideal transformer. Thank you.